Hello, AP Physics 1, it's Mr. Ng, and I wanted to take some time to go over your spring question, the spring page, and your third energy packet. So here, part A is pretty darn easy. It just wants us to draw and label the forces. So obviously we have mg, right? And we know mg. mg is, the mass is 1 kilogram times 10 meters a second squared. Oops. So the mg is equal to 10 newtons. That's pretty easy. This is an N, by the way, N. And then on top we have tension, and this tension is going to be 10 newtons. Initially, the tension is not, but it will get to equilibrium here. And next, part B. It wants us to calculate how much the spring has stretched. And here's where a lot of us made a mistake. A lot of us were trying to use the equation for energy. The spring energy is equal to 1/2 kx squared. Because you saw the spring constant, you saw this k, and then you thought of 1/2 kx squared. But the thing is, we don't know the energy, right? So we can't use this equation yet. But we do know the force. We know the force is equal to 10 newtons. So a better strategy here is to use Hooke's law, which is our lab, which is our spring lab for this unit, right? Hooke's law goes, the force of a spring is equal to K times X. And we know that force, right? That force is 10 newtons. 10 newtons is equal to our K constant, our spring constant is 50 newtons per meter times X. So X, if you do a little bit of dividing, 10 divided by 50 is equal to 0.2 meters. Done. Seems pretty easy. The next part it wants to calculate the height of the equilibrium position in respect to the floor. So here is just a little bit of a simple arithmetic. We know that this thing goes down from where it was 0.2. So this goes further down, and this is 0.2. So 0.2 plus 0.25, that means this whole thing is 0.45, but it wants this distance. It wants this one. So this is 0.45, this is 1, so it's just h is equal to 1 minus 0.45, so we're at 0.55 meters. Good. Okay, let's go over to part C. In part C, Angela makes an energy bar graph, and she is correct by starting at 0.75 joules. And here, there was some confusion here as to where this 0.75 comes from. If you recall, the spring early on was only extended 0.25, and the total height was 1 meter. So that means the difference in height between the spring and the floor is 0.75 meters. So she just did mgh, so it's 0.75 times 1 kilogram times acceleration of gravity being 10. So she got 7.5 joules. Good. This is a J, by the way. So 7.5 joules. Is there any kinetic energy in the very beginning? Is the spring moving? Nope. Is there any spring energy yet? Is it stretched out yet? Nope. So the total mechanical energy for this system is 0.75 joules. Pretty easy so far. Here, what about when it gets to equilibrium? Well, we know mgh again, right? We know that from the last part, we know that it's now 5.5 above the ground, right? This is 5.5 meters. So just doing a little bit of mgh, we know that the gravitational energy is at 5.5. Good. So what else can we figure out? Well, we could figure out the spring potential energy. The spring potential energy, this is US, is equal to 1/2 kx squared, where k is 50, so it's US is equal to 1/2 of 50. And then the displacement, if you recall, in the last part was 0.2 meters squared. So this is kind of a mess and really ugly, but this becomes equals to 25 times 0.04. 25 times 0.04 is equal to 1 joule. So that means the spring energy is 1 joule. If you add all this up, it's only 6.5. So where's the remaining 1 joule of energy? There's only one place it could be. It's got to be here. Okay? So, oops. So how did I get 5.5? I did MGH. This sucker was 5.5 meters above the ground, or 0.55 meters above the ground. How did I get 1 joule of energy for the spring, for this potential spring energy? I used my equation, 1/2 kx squared. And then how did I get the kinetic energy? Well, I just assumed conservation of energy, and it's the amount of energy left, right? 6.5 here. So there's 1 joule of energy left. Good. Okay, last part. And this last part is all about setting your zero. So Dominique and Angela have 2 different strategies. Dominique is not going to do what Angela did. Angela set the 0 as the ground, and we did our math comparing the height of the spring to the ground, where it was 0.55 meters. But Dominique has a different strategy. Dominique says, no, the ground is not 0. The ground is negative 0.55. Instead, the equilibrium point, the 0.55 that we were thinking about, that's now our 0. So she shifted her whole frame of reference down, basically. So here, let's think about our energy graphs now. That means the spring was originally above 0.55, right? It was right here, 0.2 above. That means our gravitational energy is going to be 2 joules, right? 0.2 above 0.55, 2 joules. Okay? Now when we think about it when it's actually moving, and here's the big kicker, does changing our frame of reference change the system really? By changing the way we set up our 0, do we change how fast the spring was going? No, right? It's just a frame of reference. That means the spring is still traveling with 1 joule of kinetic energy, and it still has a spring constant, not a spring constant, a spring energy of 1 joule, right? It doesn't change from the prior situation. And look, energy is still conserved. Here's 2 joules, 1 and 1, it's 2 joules again. Makes sense? So make sure you take the time to kind of explain that well. All right, Dominique changes the frame of reference so that our 0 mark is now no longer on the floor, but 0.55 meters above the floor, and the math still works out. Good.